Hey guys, okay, so we're going to talk about Objective 3 today, which is intermolecular forces, which also applies to properties of liquids and solids. We're going to split this video into two parts because just together it'd be one massive video and it just makes more sense. So part one will be types of intermolecular forces and determining what types of intermolecular forces are involved. So we'll try to keep this video short, so this will be part one, and then we'll do a part two video, which is like the relationship of intermolecular forces to liquids and solids. So we're going to get into this just to keep it nice and short and try to go through this quickly. So an intramolecular force is within the molecule itself. So intra means the force that is holding the molecule together. So the bonds that are holding it together, and you can see that we're talking about covalence here. Ionic compounds do have a force that hold them together, but there's a reason why it's not listed here, and we'll kind of talk about that on the next slide. But when we're talking about an intramolecular force, we are talking about the bonds that hold the molecule together, so in the molecule itself. These notes we're focusing on intermolecular forces. So these are the interactions between molecules, so the attractions that happen between molecule A and molecule B. So everything that we're talking about, all of the IMFs that we're talking about, so this right here is IMF, is between two molecules. So attractions between molecule A and molecule B, not the force holding the molecule together itself. So key distinction. Types of intermolecular forces. So we will talk about it in this order, which is going to be from the weakest force to the strongest force, and that's going to be London dispersion forces, dipole forces, which there's a couple different subtypes here, and then hydrogen bonding. And on all the other slides, I did this, but I forgot to do it on this slide. Be very careful with the word bonding here. So it is air quoted. We call it hydrogen bonds, but it's not. All of this between all of these applies to covalent compounds. Ionic forces do not belong on this list. So ionic forces are definitely way stronger than everything in this list. And they are a force that happens between things, but the word molecule applies to covalent compounds. Ionic compounds are a thing, but ionic molecules are not. Taking NaCl, for example, you're never ever going to find just Na and Cl together as one single molecule, because either they're going to be a large conglomerates of NAs and Cls together as like a solid, or they're going to be like floating around as dissolved ions. You'll never just find one Na and one Cl together. While this is the smallest ratio, they are, as a compound, they're just a large network solid together. So they don't exactly apply, you can't really apply the word molecule here. So again, ionic forces are a completely separate thing, so they don't really apply to IMF. IMF, we're talking about covalent compounds, the attraction between covalent compounds. All right, so starting with the weakest one first, London dispersion forces. They are a relatively weak force between atoms and elements in either noble gases or in covalent compounds, covalent molecules. So they are, relative to the other forces, they're the weakest. They're formed when you have a temporary dipole that forms. So you have electrons that are constantly moving around, and those electrons will occasionally find themselves in moments where they are clustered to one side of an atom or a molecule more than the other side, which causes this temporary force to form. So they are temporary forces that only exist for a snap second and then they're gone. The big thing here is this: everything has LDF. So, I mean, you could try to talk about like even ionics as having LDFs, but just the force difference between that and ionic is ridiculous. So really, when I say everything has LDF, I mean all covalent compounds have an LDF, no matter what. If it's covalent, it has an LDF force, and individual elements, like elemental forms of individual elements, also have an LDF. So like oxygen as a molecule has an LDF. The noble gases, helium, nitrogen, or helium, neon, argon, even though they're single elements floating around, they can form a temporary LDF. So most things have, and basically everything can argue as having an LDF because everything has electrons, and those electrons are always constantly moving to kind of occasionally clump up to one side or another. So as we go through this, really the big thing is that noble gases can do LDFs, and covalent molecules, every covalent molecule that exists has LDF, without question. So trying to look at what LDF actually is. So we have an atom example and a molecule example. The general idea is the same here. So we have atom A and atom B. These are non-polar atoms. We have non-polar molecules that just exist. Well, they all have electrons, and those electrons are constantly moving. So in atom A here, or in molecule A, the example is the same. As those electrons are moving randomly, there's going to be a snapshot moment occasionally where the electrons happen to be more on one side than they are on the other. Or if it's a molecule, more on one side of the molecule than the other. So the electrons just clump up or cluster up in one side for just a momentary second. So they just crowd to one side for a moment. When that happens, the side that has more electrons is slightly negative. The side that has kind of a bit more spacing between its electrons is more positive. So you have this temporary positive-negative force that forms. Same thing over with the atom. So again, it is instantaneous, so it's there for a second and it's gone. When this forms, atom B can either do the exact same thing at the exact same moment, so it can have a temporary movement of electrons, or atom A, because it's slightly negative here and slightly positive, can kind of just force atom B to move its electrons a little bit. So when it forms this positive here, that's going to be attractive to electrons, and the electrons in atom B might just slightly rearrange themselves temporarily to become more to one side than the other and force this to happen. Either way, you get a temporary positive negative that forms here, a temporary positive negative that forms here, and there's going to be an attraction. And same thing between molecule A and B, same idea. Electrons cluster up here for just a second. This positive end gets attracted to this negative end, again for just a second, and then those forces disappear. And these forces will pop in and out of existence randomly, and depending on how frequently it happens will determine how attracted these things are to each other. So LDF is just temporary forces that pop in and pop out. So one of the things that's worth talking about is polarizability. So LDFs, primarily when we're talking about LDFs, it's happened when we're talking about them with non-polar things, so things that aren't polar on their own. So if polarizability is essentially just saying how easy it is for these LDF forces to pop in and out of existence. So larger atoms with many electrons are more polarizable than smaller atoms. And when I'm talking about large and small here, I'm not talking about mass, I'm talking about number of electrons. Something that has more electrons is more polarizable than something that has less electrons. So when I say larger, that's what I mean. More complex compounds can do this as well. So if they have the same number of electrons, The thing that has the double bond or the triple bond or whatever in it is more likely to do this as well. This one is not quite as important for AP level problems. You'll see it in college if you take a particularly organic chemistry in college. So really, as far as AP goes, the more important one is this larger thing. So the fact that more electrons means a stronger LDF force. So more electrons means more polarizable, which means LDF forces will pop in and out of existence more frequently. So this becomes stronger. AP very much likes this word, so if you're using this to justify something, you can say that more electrons or larger elements are more likely to do this or have a stronger LDF, and they'll accept it, but they like it even more if you say polarizable. But that's just kind of semantic term stuff. So looking at this graph, again, everything here only has LDF forces because they're all non-polar entities. So you have helium, fluorine gas, bromine, which is a liquid, and then iodine, which is a solid, all at room temperature. So you can see these guys are small. They have, like helium only has 2 electrons. So very, very small boiling point, like basically absolute zero. And so very weak LDF force here because it only has 2 electrons. There's not a whole lot going on. Here, it's more complex because it's F2 instead of just He. Like there's only 1 atom here, there's 2 atoms here, so complexity went up, number of electrons went up, so slightly stronger LDF. Here we've added a whole new set of electrons, so we've gone from 9 electrons for each fluorine to 17 electrons for each chlorine, so more likely to cause LDF forces, or LDF forces are more frequent, so stronger LDF force. Both gases at room temperature. Here to here, we're going from a gas to a liquid at room temperature because extra electrons, more frequent LDF, more polarizable, so change in state. There's more attraction here than there is here, and then even more for iodine, which makes it a solid at room temperature. Again, all just strength differences in LDF. Okay, so this time we're going to look at strongest, weakest LDF, and I'm throwing some organic molecules at you. Part of why I'm doing this is because AP does this, and they do it just to freak you out. So these are different ways, these are all different organic molecules, and you guys haven't really spent any time looking at what these molecules are, like drawing these organic structures. So this is a brand new way of looking at a molecule that you haven't seen very often, and there's no reason to freak out just because it's different. So this type of organic structure here, so this particular one, there's 4 carbons, 10 hydrogens, and 2 oxygens. Well, you can see 2 oxygens and 2 of the hydrogens, but in this shape right here, we are hiding 4 carbons and 8 hydrogens. And that's what essentially all of these bumps are. So 1 carbon there, 1 there, 1 there, 1 there. Same thing here, we're hiding a bunch of carbons because there's apparently 9 carbons here, 8 hydrogens, and 1 oxygen. And I only see a little bit of that. And then same thing here. So don't freak out just because it's drawn like this. Organic molecules are drawn like this to emphasize key sections. So you're seeing just the parts that are like notable or worth mentioning. This is probably a more common way to look at it. So this is slightly better for you guys, but again, it's large and it's these carbon chains that you're not used to dealing with. So labeling strongest to weakest LDF, I'm guessing you guys are probably still struggling trying to do that. One last way to look at this is like this. We can just write it out. Well, organic, you generally write out the molecule in such a way to kind of emphasize its structure. You have OH, CH2, 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 look, HO, CH2, CH2, CH2. They will throw things at you like this just to kind of freak you out. So let's go back and look at it this way. When we're talking about LDF, I said larger molecules and atoms, more electrons, and more complex. Well, this formula is C2H3N. It is easily the smallest molecule of the three. It has the least number of electrons because it has the least number of elements. So this guy right here is going to be our weakest LDF. So he is for sure the weakest because he's the smallest, least number of electrons, least polarizable, etc. Between these two, this guy is slightly larger than he is. Yeah, he has a couple more hydrogens and one more oxygen, but 4 carbons versus 9 carbons. So he's not only the largest, he has the most electrons, and if you compare the two, you have all these double bonds in here, he's also the most complex. So between these two, he's our strongest, he's kind of our middle guy. So strongest LDF, middle LDF, weakest. So 1, 2, and 3. Pretty straightforward. Again, we could just count up things here, 1, 2, 3, 4 carbons, 9 carbons here. Even though this is written out longer, this is larger and more complex. Okay, dipole forces are the next one. So of the 3 different LDFs, this is number 2. This is also the one that people usually get most confused with. So dipole forces are molecules that have one side that is permanently slightly positive and one side that is permanently slightly negative. So it is not ionic. There's not a formal positive and negative on this thing, but one side just slightly is holding on to more, or is hogging the electrons more than the other side. So a dipole force is going to exist between 2 molecules that both have this going on. You have one molecule that, again, has one side that's slightly negative, one side slightly positive. Same thing with this molecule over here, so there will be a permanent attraction. The slightly positive side will always be attracted to the slightly negative side. So an example of this is hydrogen fluoride. So hydrogen has clearly less electrons than fluorine does, and fluorine is more electronegative than hydrogen. The difference here is this is 2.1 and this is 4. So there's a large electronegativity difference here. So the electrons, even in this bond, are getting pulled way more towards fluorine than they are towards hydrogen. So you draw an arrow from the least electronegative to the most electronegative, so the arrow points this direction because that's where the electrons are getting pulled. Draw a line right here to say that this side is slightly positive, this side becomes slightly negative, and this molecule will always look like this. You'll always have a positive here and a negative, a slight positive here and a slight negative here. And so it looks just like this. If there was another HF floating around, it would look like this. Well, so this side would be F, this side would be H, and there would be that same attraction. So the hydrogen side of this molecule will always be attracted to the fluorine side of this molecule. So going back to our organic guys, these are the exact same ones earlier. We can still label dipoles. So while these guys have different LDF forces, they also have different dipoles on this whole thing. So a dipole exists between any molecule, it exists across any bond that has an electronegativity difference that is greater than 0.4. I would say greater than or equal to. In general, anything that is exactly a difference of 0.4 is going to either be an extremely weak dipole or pretty much non-existent. So we have lots of bonds to deal with here. But if you look up here, the electronegativity between carbon and oxygen, or carbon and hydrogen, well, this is 2.5 and this is 2.1. So this is exactly meeting the 0.4 criteria. And since it's just such a weak difference compared to anything with oxygen or nitrogen, we're going to just say that any carbon to hydrogen bond is nonpolar. Any bond that involves oxygen or nitrogen, because these values are so large, will be. So let's just focus on anything involving oxygen or nitrogen. So down here, well, we have carbon and nitrogen. So drawing an arrow from lowest electronegativity to highest electronegativity, the electrons will be pulled this direction, which means that this side is slightly positive, this side slightly negative. Over here, again, all these hydrogen carbons, we're going to ignore all of these things. Carbon to carbon is nothing because it's the same value. So here we're going to have a pull this direction because we're going from 2.5 to 3.5. And then here, well, we have that same carbon to oxygen bond, and we have the hydrogen to oxygen bond. So we get pulled in this direction. Okay. So I'm going to color code this a little bit. So this side right here, we've essentially said is nonpolar. So all of these red sections, this is nonpolar part of the molecule. This is the polar part of the molecule. So we have a dipole right here. So this dipole is slightly negative on, or slightly positive on this end, slightly negative on this end. Across here we have another dipole. You can see I drew an arrow right here, and we said that like this is only a difference of 0.4. So it's really not that strong, but because oxygen's here, it's going to kind of add a little bit of an oomph. So we'll consider this carbon to hydrogen polar, but not any of these. And honestly, if you didn't consider this one polar, it wouldn't really change a whole lot. Up here, you can see same thing, a pull this direction and our pull this direction, but I made these arrows much larger. The reason I did that is, well, the difference here is 3.5 compared to 2.5, so that's a difference of 1. The difference here is 3.5 to 2.1, so this is noticeably stronger. And this is a special type of dipole we'll talk about in a couple of slides here, but this is the strongest of all the dipoles here. So this one is way stronger than this one. So adding in all of those values, we have these 1.4s, so slightly positive here, slightly negative here. There's also the slightly positive on the inside here, but because it's in this non-polar stuff, I won't really bother with it. And then across here, same thing, slightly positive, slightly negative, slightly positive, slightly negative. You can see that I put the positive all the way down here, not on carbon, because of this extra little bend right here. So if we were to try to label these or organize these, I would definitely say that this guy is the most polar of all of these. Not only does he have the strongest bonds, the strongest dipoles, he also has one on each side of the molecule. And yeah, you do have this red section in the middle, but he has two very strong dipoles on the outsides. This guy's relatively small, like half of the molecule is polar, but it's only a difference of 0.5, and there's only one of them. And then over here, you do have this polar thing happening right here, but you have this big non-polar mess to deal with. So this molecule is easily the most polar. It also has a relatively strong LDF, like it's not as strong as this, and it's not as strong as this, and it's a bit stronger than this. So overall, this guy has a decently strong LDF, noticeably stronger polarity. So you would see those two come into effect here. So he's the most nonpolar, strongest LDF. He's not super strong polar, not super strong LDF, and definitely the most polar. Okay, to try to speed this along a little bit. So ions can also be attracted to dipoles. Since a dipole is a slightly positive side, slightly negative side, those things are attracted to anything with anything resembling a positive or negative, and ions are straight up positive and negative. So if I throw salt into water, well, salt has a positive ion and a negative ion. Negative ion will be attracted by all of the positive hydrogens. The positive sodium will be attracted to all of the negative oxygen, or the slight negative side on oxygen. And you can kind of see this whole thing happen. Okay, sorry about that. That was one of my honors kiddos walking in. So yeah, ions will also get attracted to dipoles, so that's why water dissolves salt, because the dipole of water is attracted to the ions in salt. And then hydrogen bonding, you can see again air quotes, because this is not a bond, it is just something that we call a bond. Hydrogen bonding is an attraction between molecules that have a certain requirement. So it's a very strong type of dipole. So these are very polar bonds, and they happen anytime you have hydrogen attached to nitrogen, oxygen, or fluorine. That hydrogen is going to be very much attracted to any molecule that has N, O, or F in it as well. So you can see here you have this hydrogen to oxygen that is an actual bond, and because of this actual bond, the dipole between these two is strong enough that this hydrogen is very strongly attracted to this oxygen. So the hydrogen bond is the attraction between this special hydrogen and this oxygen. So examples of hydrogen bonds, and these are more just kind of semi-complex molecules. Here's hydrogen attached to chlorine. These hydrogens cannot hydrogen bond, again air quote. They don't have a dipole strong enough to make this level of attraction. This hydrogen, because it's attached to nitrogen, which is very electronegative, the dipole force here, let's draw that dipole force out really quick. This dipole force right here, oh, that was a bad one. There we go. Is strong enough to make this slightly positive and this slightly negative, and it's strong enough that any time this hydrogen comes close to another nitrogen, another oxygen, another fluorine, there will be a strong dipole attraction here. You can see that here it's that same hydrogen, well now it's attracted to the oxygen and water. And this hydrogen is attracted to the nitrogen in this same compound. So hydrogen bonds are a strong IMF force between a specialized hydrogen and nitrogen, oxygen, or fluorine. So looking at things, nonpolar covalent compounds only have LDF forces. Polar covalent compounds have LDF forces and dipole forces, or a special dipole called hydrogen bonding. And ionic forces are so much stronger that they straight up do not count anywhere near this stuff and are not molecules. Ionic compounds are not molecules, so this is just insanely strong. And we do not think about it in terms of IMF. So this is what we think about for IMF. The difference between nonpolar covalence and polar covalence. Looking at it again, in terms of strength, LDF forces, dipole, which is that induced dipole force, ions being attracted to induced dipole forces, actual dipole forces are stronger than all of this. Hydrogen bonds are stronger than regular dipoles, and then an ion and a dipole being attracted to each other is usually stronger than hydrogen bonds. If an ion is involved, it's usually a pretty strong attraction compared to dipoles of some kind. Ions, again, don't come into play. They are so much stronger that they are actual forces. These are not intermolecular forces. These are straight up intra forces of some kind, and different ballpark. Okay, so that's the end of this video. I tried to keep it as short as I could. We'll talk about part 2. I'll try to fly through that too, and see you in part 2.